So one of the things with each of these three numerical invariants that we look at is how do they behave with respect to the connected sum. So if I have two knots, K1 and K2, then I'd like to know, for example, what is the unknotting number of their connected sum? What is the bridge number of their connected sum? And what is the crossing number of their connected sum? And of the three numerical invariants, only the bridge number has a nice, predictable relationship. That the bridge number of the connected sum of two knots is what you get when you add up the bridge numbers of each and then subtract one. And I'd sort of show a diagrammatic proof in the video of why that should be true. The -1 happens because when you connect two knots together, they can share one of the bridges that they used to have independently from one another before you took their connected sum. So this is the one where we can put an equal sign here, and now we have a recipe for computing the bridge number of a connected sum. Whereas the other two of these invariants, we don't get so lucky. So for the unknotting number of the connected sum, the best we can say is that it's less than or equal to the unknotting number of K1 plus the unknotting number of K2. And similarly, for the crossing number of K1 connected sum K2, less than or equal to. And exactly in what cases equality holds for these is kind of an open question in knot theory. It's something you could still do knot theory research on if you were interested in it. And it's known for some large classes of knots when equality holds. For example, the unknotting number. Actually, let me go to crossing number. The crossing numbers add on the nose, so this is an equal sign, in the case where K1 and K2 are drawn in an alternating projection. Right? So if they're alternating and we connect them up, then the crossing numbers just add together. But if they're not alternating, then we don't know. Similarly with the unknotting number, K1 connected sum K2, the case in which equality holds there, that's escaping me here, but it's not currently known in general whether we can put an equal sign in one or the other of these places. So one of the things that you could do, it would be significant for somebody to find an example of a pair of knots which showed that less than is true. If you could find a knot K1 and a knot K2 where the unknotting number of their sum is strictly less than the unknotting numbers added together, that would be a huge deal. You could instantly publish that paper, right? Probably attach your name to the theorem or something like that. Same thing with the crossing number. We just haven't found an example yet of a pair of knots in which that actually happens. We can guarantee less than or equal to holds for each of these, because certainly if I take the connected sum of two knots together, I don't ever need to use more than the sum of this many crossings to represent it, because I'm not creating or destroying any crossings when I make a connected sum. And so we're never going to need more crossings than the sum to represent a knot, but we could, potentially there is a way to rearrange the knot with Reidemeister moves or planar isotopies or whatever that reduces the number of crossings in its minimal projection. Same thing with the unknotting number. We can always unknot a connected sum of K1 and K2 by switching enough crossings on K1 and enough crossings on K2 to make each of them individually into the unknot. But we don't know whether there's an example where connecting the two knots together provides an opportunity for a smaller number of switches to still unknot the whole thing. So it would be a huge deal if you were able to prove that there's an example where the less than actually holds. Or, conversely, maybe there is no such example, and maybe these are actually equality for broader classes of knots than are currently known that it's equality for. But those are two big unsolved questions in knot theory right now that you could do some really interesting research on. So you just took apart a couple of knots. We had the 6-2 knot, which was the one on the right here, and 7-1. So this is a 6-crossing knot. This is a 7-crossing knot. And for 6-2, you found a way of unknotting using only a single crossing change. Mm-hmm. But it wasn't your first guess. What was your first approach?
The top right.
So you looked at the one up here and then said, all right, what happens if I swap that crossing? Well, then I'm going to have this nice over right here that I can unpoke and then untwist. But then you still ended up with these crossings over there that you couldn't get rid of with that one. But if you switch this one here in the middle, which is weird, it seems like that wouldn't, I mean, just by looking at it, doesn't seem like it would be enough. But what actually happens? So how can we?
I don't know. I just kind of pulled it up and it
So if we sort of draw it as though it's going like this now, then yeah, actually a lot of sort of complicated untwisting kind of has to happen at once. But if you actually diagram it out or use a rope or whatever, you find out that one crossing change in the middle there makes the whole thing fall apart. And so that's the one case when we know for sure what the unknotting number is going to be. Unknotting number for this is 1. Because there's no way to have any smaller number of unknottings, except what's the only knot that has an unknotting number that's smaller than 1?
Unknot.
The unknot, yeah. The unknotting number of the unknot, of course, is 0. But 1 obviously is, we can't get any lower than that unless the knot is the unknot. All right, so that one we know for sure then that the unknotting number of 6,2 is equal to 1 because you found specifically an example of a crossing that can be undone in order to make that happen. 7,1, so you found a way of unknotting it by reversing these 3 crossings.
Yes.
Right? And so that tells you that the unknotting number of 7,1 is?
We believe that's the one.
Yeah, we don't know if it's equal to 3, but we can say for sure that it's going to be less than or equal to 3. Right? So finding a way of unknotting it by switching 3 crossings shows that the minimum number of crossings necessary to unknot this knot is 3. Or is going to be no more than 3. Right? But it's possible that there's a way to do it with fewer than 3 crossings. One of the things about this knot that we were talking about, though, is that all the crossings are kind of equivalent to one another in 7,1. Right? There's none that are kind of set apart from the others. And so chances are you found a way of unknotting it with these 3 crossings, no 2 of which were adjacent to one another. And there's a lot of other sort of choices of 3 crossings that we could use here to do that. But if we tried to do it with 2, you can, if you try enough 2 crossings, you'll kind of figure out what the pattern is. That 2 is never enough, it turns out, for 7,1 to undo this one. So it does turn out, but it's not obvious from the work we've done today. We don't have a proof anyway that this unknotting number is equal to 3, but in fact it is. And of these 3 different knot invariants for today, I feel like the unknotting number is the slipperiest one, right? Because you never know for sure whether or not you found the minimum, unless you have some really profound proof. And even for some knots with relatively small crossing numbers, like 8, right? Adams talks a little bit about the example of 8,3 and how the unknotting number of 8,3 is 2. But the fact that it is equal to 2 actually required a super high-powered proof with some sophisticated geometric techniques that was only discovered, a handful of years ago. And when I say handful, I guess it was the 80s. So that feels like a handful of years ago, but in reality, it's 30-plus years. But yeah, let's not say any more about that. So it's a tough problem, and you can never be sure unless you have this really challenging proof. And it also doesn't feel like there's a terrific pattern to it. The 7,1 seems like a pretty simple knot, right? It just has this single-digit Conway notation. It's just 7. And yet we have to reverse a lot of its crossings to make it fall apart. Whereas 6,2 would on the surface look more complicated, but in fact you undo one of its crossings and it's already done. So it doesn't seem like there's a lot of regularity or a lot of pattern to it. If you could find such a pattern, you'd be in real business. You could have a theorem named after yourself. But there's still a lot that we don't know about how these different knot invariants interact with one another.